Hello, my name is Jeferson Gonzalez, a PhD student at the Karlsruhe Institute of Technology, and today I will present you our recent paper titled The First Concept and Real-World Deployment of a GPU-Based Thermal Covert Channel, Attacks and Countermeasures. A covert channel is a communication means typically between two malicious applications through an unconventional or hidden channel. The first application, known as a malware, has access to private information but no I/O or direct communication with other applications. It takes the role of a transmitter. The second application, known as a spy, doesn't have access to private data, but it could have access to I/O and possibly other external applications. A thermal covert channel is a type of covert channel created via changes in the temperature produced normally by controlled CPU activity. In the example figure, we can see an 8-core system. Application 1, the transmitter, and Application 2, the receiver, are executed on different cores. When Application 1 intends to transmit a bit of 1, it raises the temperature of its core by doing some processing for some time. Because of the closeness of the cores, this temperature increase can be seen by the receiver on its own core thermal sensor. This way, the applications have communicated through heat transfer. In recent years, GPU computing has risen as an efficient way to accelerate computation in several domains, such as high-performance, cloud computing, and machine learning, due to its highly parallel nature. Because of this, the GPU has been included in security-critical applications as well, as part of secure and trusted zones. Due to their applicability to sensitive data, GPUs have been recently the target of timing-based side and covert channels. However, until this work, it remained an unconsidered resource for thermal covert channel attacks. In this work, we proposed the first concept of a GPU-based thermal covert channel. But before getting into details, we should discuss the challenges that make GPU thermal covert channels unique. First, in the attack implementation, GPUs are comprised of hundreds or even thousands of cores, typically with a single thermal sensor for the whole device. This means that raising the temperature involves highly parallel computation, and cooling it down requires more time than it would take for a CPU. This, in consequence, produces lower transmission rates in GPU-based thermal covert channels, while affecting implementation aspects such as packet sizes. Secondly, on the countermeasure side, traditional CPU-based techniques against thermal covert channels, such as dynamic voltage and frequency scaling, produce much bigger performance degradation when affecting GPUs, as I will show further in this presentation. Our contributions for this paper are the following. We are the first to propose using the GPU to create a thermal covert channel for heterogeneous CPU-GPU computing systems. We develop a real-world implementation of the new GPU-based thermal covert channel that evades existing detection techniques in the state-of-the-art by exploiting a previously unconsidered computing resource. We analyze and expand current CPU-based countermeasures for thermal covert channels to tackle the new GPU-based attack and measure their performance impact on other applications. Finally, we propose a new thermal-aware DVFS countermeasure to GPU-based thermal covert channels that mitigate the attack while producing less performance loss than the state-of-the-art solution on a set of compute-intensive GPU benchmark applications. To introduce our contributions, first let's start with the transmitter application for the GPU-based attack. The transmitter sends packets of bits and encodes them as temperature variations. When a packet of data needs to be sent, the transmitter first applies a Hamming error correction code. After that, a 2-bit header is appended to the packet. The first bit of the header signals the start of a transmission, while the second one is used to identify the sender and the receiver in a bidirectional communication manner. Then, the newly formed binary packet is further encoded with temperature variations. The bits of 1 are processed with a multi-threaded CUDA busy waiting kernel, while the bits of 0 are encoded by slipping the threads. To avoid temperature accumulations that may affect the transmission, we employ a return to 0 scheme, where after raising the temperature for a bit of 1, we let the GPU cool down to its base temperature before transmitting the next bit. We also provide an on-off keying modulation technique, which takes the channel to a higher frequency carrier, making it more robust against low frequency noise. The receiver application oversees the decoding of data from the GPU thermal sensor. To do so, it first reads the sensor data and applies a filter to it. The purpose of this filter is to reduce the lower frequency noise, as well as remove variations due to the sensor's precision. After the filtering, the deserializing process begins. Here, we detect the header's starting bit by computing a delta between the current and the previous temperature measurement. When the starting bit is detected, we demodulate the temperature data by taking windows of fixed length data points and comparing the magnitude of the signal against a predefined threshold. When all the bits from the packet have been demodulated, we check that the header is correct and remove it from the packet. Packets with incorrect headers are discarded and an error is marked. After the header is extracted, we apply the error correction decoding to extract the original data. If an error remains after correction, the packet is again marked as incorrect. On the countermeasure side, we propose a new thermal-aware DVFS policy. Different from state-of-the-art approaches, this new technique considers the current temperature of the GPU to set a new frequency when blocking the attack. This allows us to quickly mitigate the attack while reducing the performance loss on other applications when active. In the algorithm, we show the simple functioning principle of our policy. While the policy is active, we compare the current GPU temperature against the normal used target temperature. If the temperature is higher, we decrease the frequency by the minimum allowed step by the device. If that's not the case, we boost the GPU by increasing the frequency by the same step in order to improve the performance of applications using the GPU. Finally, we clip the frequency to the minimum and maximum values allowed by the device. In the figure to the left, we can see the policy in action. As depicted around 150 milliseconds, when the temperature increases over the 56-degree target, the frequency starts decreasing, which in turn decreases the temperature. Once the temperature hits the target, the frequency starts increasing again. Please note that the temperature variations are small due to the countermeasures and centered around the target temperature, which makes it harder for the receiver to correctly decode the data. To evaluate our new attack and countermeasure, we chose two real-world platforms: an embedded NVIDIA Jetson TX board with an integrated GPU, and a general-purpose NVIDIA GeForce RTX graphics card as a dedicated GPU device. The characteristics of these platforms are shown on the right. Notably, the platforms are very different from one another even in the operating system used. To maintain consistency with the attacks and countermeasures, we employ the same sampling frequency of 500 Hz for both platforms. As evaluation, we first measure the effectiveness of the attack itself in terms of transmission rates in bits per second, as well as bit and packet error rates for both platforms. As seen in the table in the upper right, we achieve a maximum of 8.75 bits per second for the Jetson platform. In the figure on the lower left, we can see how a packet is encoded through the temperature signal before filtering. In the table on the lower right, we show the bit and packet error rates for different packet sizes. As seen, for a small packet size of up to 16 bits, we achieve less than 5% packet error rate. However, as the packet size increases, we can see how the error rate increases drastically because of the temperature accumulations and the effort to heat and cool down the GPU. This is a major difference over CPU-based thermal cover channels. To evaluate our new countermeasure, we extend state-of-the-art CPU-based countermeasures to the GPU domain. To measure the effectiveness of the countermeasures when mitigating the attack, we select the following approaches to compare against our new thermal-aware DVFS policy. The baseband noise approach consists of a constant parallel GPU processing. The narrow band noise is similar to the baseband, but it is toggled on and off periodically at the frequency of the channel. For the DVFS-based countermeasures, we took the down-up rate or beta-based approach from the state-of-the-art, using high, intermediate, and low beta values. In the figure, we can see for the RTX platform how our thermal-aware DVFS policy is as good as the other solutions when blocking the attack, producing high bit and packet error rates. An interesting effect happens on the embedded Jetson TX2 board. First, our solution is a bit less effective than it was on the RTX board, But as we will see shortly, we trade off effectiveness for a much better performance. Notably, the beta equals 1 or low beta implementation for the state-of-the-art performs poorly when mitigating the attack, managing to produce only 50% of the packet error rate in the attacker. Finally, we compare our thermal-aware DVFS solution against the other DVFS techniques from the state-of-the-art in terms of overhead on other applications. For this, we run a set of applications from the Rodinia GPU benchmark and measure their performance loss due to the DVFS policies. In the figures, we can see the performance loss for both platforms. On the RTX platform, our solution outperforms all the implementations of the state-of-the-art techniques by more than 2 times. On the embedded board, our solution again outperforms the high and medium beta implementations by 2 times. Note that while the low beta implementation has a lower performance loss than our solution, it failed when blocking the attack as we just previously discussed. Notably, all solutions performed much worse on the embedded board than they did on the RTX, which is more capable GPU. Since most of the thermal covert channel attacks have dealt with general computing devices, we consider that their implementation on embedded devices should be given more attention. The same is true for countermeasures and the overhead that they produce on the embedded platform. In this paper, we have presented the first approach for a GPU-based thermal covert channel attack. We analyzed and evaluated our attack on 2 different real-world computing platforms to show their general applicability. Our results show for the first time that a GPU-based thermal covert channel is feasible with high enough transmission rates and low enough bit and packet error rates that are comparable to existing CPU-based attacks. Moreover, we analyzed and extended existing countermeasures to the GPU domain. We demonstrated how our implementation of the extended countermeasures successfully blocks the attack at the expense of added overhead in the system. Finally, we have proposed a new thermal-aware DVFS countermeasure that mitigates the attack while causing 2 times less performance loss than the state-of-the-art DVFS countermeasures on a set of benchmark applications. With this, I conclude my presentation. Thank you for your time. For more information about our research and recent publications, please check out our webpage.